Now that we understand the definition of an operation being a binary operation, we can get to, by and large, the most important definition we will learn all semester, which is the definition of a group. It's a big, long definition, so make sure you stay with me for all of it, because every symbol, every word, every little detail in this definition is important. So let's dive in. Throughout this definition, G is going to be a set, and dot is an operation of G. We're going to say that G is a group under dot if the following 4 properties hold. Our first 2 properties are properties of the operation dot. The first one, which I've labeled 0, which we'll talk about in a moment, the first property is, you guessed it, that dot operation needs to be a binary operation on the group. The second criteria is that that dot operation needs to be an associative operation. In other words, whenever we pick 3 elements of the set, no matter what those 3 elements are, we need it to be the case that A dot B dot C is equal to A dot B dot C. Now the pauses there were to indicate where the parentheses are in this equation. Notice that although the parentheses have changed location from the left-hand side of the equality to the right-hand side of the equality, the order of the letters has stayed the same. And that's a very important thing, which also we will talk about in a moment. The next 2 properties are properties that the set must satisfy. The first is that there exists an element that we call E in the set, so that for all elements of the group, A dot E is equal to E dot A is equal to A. And this element E that must exist in the set is called the identity of the group. You might have a moment where you think that this E ought to be an I for identity. We choose not to use that notation for a couple of reasons, the first of which is that the letter I is so frequently used as the square root of -1 in mathematics that using it for other purposes could be confusing. But the real reason that we use E to represent the identity here is because the German word for identity starts with an E, and group theory was born in Germany. Many of the words we use in group theory come from the German language. The same is true actually about why we use the letter Z to represent the integers. It's not for Z integers, it's because Z represents Zahlen, which is the word in German that is used to denote the integers. Moving on, the last criteria in order for our set G to form a group under the dot operation is that for all elements A in the group, there exists an element B in the group so that A dot B is equal to B dot A, both of which are equal to this special identity element E. For a given A, the element B that works in this special manner is called the inverse of A in G. So there you have it. Those are our 4 criteria. 2 criteria that belong to the operation and 2 criteria that belong to the set. Now, let's get back to the strange numbering scheme that I've used for these 4 criteria. Every now and again, you'll look for a different resource to help solidify your understanding of a concept, and you might find it confusing if you opened up an abstract algebra book and they only listed 3 properties required to be a group. Very frequently, this property that I have labeled as property 0 is put into sort of the stem of the definition, where I was very careful in the stem of my definition to say that dot was an operation on G. Some books will say suppose G is a set and dot is a binary operation on G. And if you put the word binary up in the stem of the definition, you don't need this one. And then they'll list off these 3 properties, 1, 2, 3, as the definition of a group. So don't be shocked if you open up another resource and it says you only need 3 things to be a group. Secretly, that fourth assumption is still there, it's just not listed explicitly. And since I really wanted my numbering scheme to line up with what is typically the case in other books, I made that property 0. The other thing I'd like to point out is that I was very specific to say notice that the A, B, and C are all in the same order, and it's the parentheses that have moved location when we talk about the associative property. Whenever you have a definition in mathematics, it's nice to think about what properties are not there in addition to the properties that are there. And what I would like to point out is that we have not required our operation to be a commutative operation. In other words, I have not required that A dot B be equal to B dot A for all A, B, and G. That is not a requirement of groups, and so I am not allowed to switch the order of any of these letters via the definition of a group. As you're well aware, there are many operations, in fact binary operations, that are commutative operations. That is a property that many things satisfy. We may very well have some groups whose operations are commutative. And just as when we had 2 different words for a binary operation, and that places the emphasis on the operation, and we could also talk about a set G being closed under an operation, we can do the same thing with groups that have a commutative operation. If we want to shift the emphasis to the set in that situation, we would call such a group an abelian group for the mathematician Abel, who is credited with first having studied groups with this additional property.